Hello, today I'll be introducing a new method to compute the position of small bird equipped with data logger using atmospheric pressure. Most species of bird weigh between 6 and 400 grams, and it's commonly accepted that the tracker used to study their movement shouldn't weigh more than 5% of their weight. Bird over 400 grams can be equipped with traditional GPS providing high accuracy, though recent progress has seen birds as light as 100 grams being equipped with a satellite tag. Below 100 grams, however, no transmitter can be added to the tracker, such that the bird must be recaptured to retrieve the data. So half of the species worldwide still rely on small data logger using mostly light level measurement for positioning. Because light intensity varies with environmental condition, the accuracy of such data remains quite coarse. Calibration can help for account for this uncertainty, but the change in topography, vegetation, or birds' behavior mean the calibration can be quite wrong in other locations. Today, we are excited to present our work using pressure sensor to determine the bird's location. Because pressure sensor can be as light as 0.4 gram, this opens up opportunity to track bird as small as a kinglet, firecrest, or sandbird, and with precision up to 10 to 100 km resolution. I'll start by explaining how we can use the pressure time series measured by these devices to produce a probability map of position. This is what the time series of pressure measurement from a geolocator look like. You can pick up the long stationary period at breeding and non-breeding site, as well as the migratory flight characterized by the drop in pressure corresponding to high altitude flight. What is of particular interest for us is this relatively small yet diagnostic variation of pressure while the bird is stationary. This variation constitutes a unique signature which can be matched with a weather reanalysis database. Pressure is a central driver of our weather system and as such a key variable in weather model. Reanalysis data such as Error 5 provide high temporal and spatial resolution data of past pressure measurements. To give you a sense of the match, let's compare the pressure measurement of our geolocator with that of Error 5. Because we know the location at the equipment site, we can retrieve the pressure time series of the weather reanalysis data, and we observe a striking match in their temporal variation. But there is still a significant offset in the absolute value of pressure. This is because if we look at the fine scale DEM within the Error 5 grid cell, we can see a wide range of elevation. We actually know the exact location of the bird within that grid cell so that we can correct the Error 5 time series for that specific elevation. The resulting time series now show a perfect match in absolute value as well. Now, let's assume that we don't know the position of the bird, and we'll see how the method can estimate a probability map of position. The method used two distinct information for every Error 5 grid cell. Here, we'll use two different locations in dark and light blue to illustrate how it works. Firstly, we compute the temporal mismatch. Because we don't know the exact altitude of the bird within any particular grid cell, we can rely on the absolute value. So we shift the time series. We then compute the mean square error between the time series and convert it into a probability map. Secondly, we check that the range of pressure measured by the geolocator falls within the range of altitude present within each grid cell. To do that, we compute the max and min altitude within each grid cell using the fine-scale digital elevation model. We can then simply check whether the time series fall between these two lines. If not, we exclude the cell by masking the probability map. This approach results in a probability map for each stationary period of the bird's journey. In our study, we assessed this method using 16 tracks from 9 different species, showing a wide range of migration strategies. Using the known location, we can validate the position retrieved from the pressure data and compare them to those derived from light. For each track, we measure the distance from the most likely position estimated from light and pressure. We found that pressure-derived positions are 3 times more accurate than light. Note that light is actually calibrated at this location, while pressure does not require any calibration. It is important to note that the shape of uncertainty provided by this method is not ellipsoidal. In this example of a mangrove kingfisher in Tanzania, this area with hilly topography can significantly reduce the uncertainty. And when thinking of habitat use, this came handy, as habitat is also distributed according to elevation profile. I'll now talk about the graphical model. The aim of this model is to compute the overall trajectory of the bird, combining data from light, pressure, as well as flight distance including wind data. This graphical model replaces the traditional approximate and iterative MCMC model with a fast and exact, at least mathematically, trajectory model. Let's first have a look at the various information at hand about the trajectory of this great reed warbler with the shiny app. For each stationary period, we have the map of probability according to light, pressure mismatch, and pressure threshold. We can thus combine this map into a static probability. For the next stationary period, which lasts only 1 day, the light data is poorly informative, and pressure mismatch is also not very precise. The pressure threshold, on the other hand, provide only a few options along the coast, so that once combined, all this information can narrow down the possible location greatly. What we are missing here is the information coming from flight duration. Assuming a certain ground speed, we can draw the distances that the bird would have flown from the previous stationary period and to the next one. In this case, indicating that the bird likely crossed the Adriatic Sea only on the next night. You can explore this app following this link. To explain how the graphical model works, let's look at a synthetic example where the bird moved from the top left to the bottom right in 4 stationary periods. We can represent this trajectory as a graph where the position at each stopover is represented by a node and the flight as an edge. In order to keep the computational cost low, we filter and trim the graph to remove unlikely nodes. We then build the graph containing all possible transitions. Finally, we compute the average wind speed that the bird would have experienced for each edge using the ERA5 database. As we know the time of departure and arrival, as well as the pressure during the flight and thus elevation, we can retrieve the wind speed with high accuracy. We finally compute the airspeed and estimate a probability for each edge. We compute 3 main outputs from this graphical model, illustrated here with a trajectory from another great reed warbler. The first one is the most likely path. The second is the probability map for each stationary period, accounting for all information, including wind and airspeed. And finally, we also simulate possible trajectory according to the model. Here are the same 3 outputs for an Eurasian Niger migrating to southern Congo, and a short distance intra-African migrant, the woodland kingfisher, and lastly, a hoopoe. An interesting output of the model is that we can easily extract the average wind speed of each flight and analyze wind support during migration. Over all our track, we found that wind direction can often explain detour in the bird's trajectory, while wind support was strongly correlated with ground speed. In this last section, I'll briefly present the R package GeoPressureR, which can be used to apply this method to your own data. This R package provides all the functions needed to apply this method. We also provide a step-by-step guide in the form of vignettes, including text, code, and illustration to explain the entire process, from the labeling of the data to the computation of the probability map of pressure and light, and finally the creation of the graph and the computation of the 3 outputs. To kickstart your own research, you can use this GitHub repository template. It provides the backbone R folder project with this folder structure for data, the R code for the analysis, essentially the same as in the vignette but in a more compact format, and the reporting tool to create an automatically generated website for each track, containing all the figures, allowing for easy share of your outputs. This project structure should help you troubleshoot issue and share code for analysis with other people. And with this, I'll finish with this animation of 5 woodland kingfisher. This is the dataset with which the whole project started, when I realized that reanalysis data was good enough to match the position of the birds. Feel free to reach out if you have any question or would like to try the method on your data. I'll be happy to provide more guidance. This work would not have been possible without the help of my collaborator, and a special thanks to Mathieu Gravey for his assistance in the numerical implementation.